Good morning, everyone. I'm Hieu. I'm a PhD student in INRA in France, and today I'm very glad to be here and to show you one approach for improving sustainable livestock production, which is about detection and characterization of the response of growing pigs to perturbation by using feed intake. So first of all, why are we interested in characterizing the perturbation? Well, it is because the current pig farming is facing too many environmental perturbations. For example, heat stress or sanitary challenge. Those perturbations decrease the performance of the pig and also the incomes of the farmer. Therefore, improving robustness of the pig so they can cope better to the environment is seen as a promising genetic strategies. And many attempts were already made to quantify and then to select the animal for robustness, for example, by focusing on some certain traits like heat tolerance or disease resistance. However, those approaches only focus on one particular perturbation, and it is difficult to quantify, to measure them. And recent study, on the other hand, show that the robustness also includes multiple elements such as the rate of respond to and recover from perturbation. So those things together make robustness very complex and difficult to quantify directly. So we aim that we can find a new and simple trait that indicate robustness in general, and which is independent to the origin of the perturbation. And then perhaps the geneticists, they can pick up and use in their breeding program. And we see the potential to do so by using a voluntary feed intake because of 4 reasons. Firstly, measuring feed intake is a non-invasive method. Secondly, with the development of modern monitoring technology, such as this automatic feeder, feed intake now can be recorded automatically, individually, with a very high frequency and in a large group. And thirdly, the impacts of perturbation on the pigs can, the impact of the perturbation on the feed intake can be observed very quickly. For example, this graph indicates the daily feed intake of the growing pigs at a function of time. And although daily feed intake vary a lot from one day to another, we still can easily observe a huge reduction in this period. And finally, almost all perturbations have the very common consequence on the pig, which is decreasing the feed intake. Therefore, the objective of our study was to develop a generic model which can detect the negative perturbation, or in other words, the perturbation which decrease the feed intake. And then we quantify the response of the pigs to that perturbation in terms of resistance. For example, to what extent the pig was affected by the perturbation, and in terms of resilience, how fast the animal can recover when the perturbation is over. The model only used daily feed intake as the only response variable. So now I'd like to explain to you why we can detect perturbation by using only feed intake data. So this graph indicates the cumulative feed intake of the pig as a function of time. And as the pig is growing up, the curve is increasing. Nevertheless, we can observe a slowdown in this period. We don't know what made this slowdown or what was the origin of the perturbation, but the response of the pig can be observed through the feed intake data. And to be able to pinpoint this slowdown, we need a benchmark. Therefore, we hypothesize that there is the target trajectory of the cumulative feed intake, which is equivalent to the amount of feed a pig designed to consume in non-perturbed condition. And therefore, the deviation from this target trajectory can be seen at the potential period of perturbation and can be quantified in terms of magnitude and duration. But how to identify this trajectory? So let's suppose if I fit a quadratic function to the cumulative feed intake data, and we hypothesize that this average curve is the combination between the target trajectory and the data due to the perturbation. And therefore, the target trajectory can be identified by excluding all of the data due to the perturbation. So if you have a close look at the graph, you see that there are a series of data systematically lies above and below the curves. And the statistical points of view, the residuals of these data are autocorrelated with each other. So therefore, we apply a statistical test to check for the autocorrelation. And if the result is significant, we remove all of the data with negative residual. And we fit again the quadratic function to a new data set. And you see the curve is already shift upward. And we check again the autocorrelation. And if it's significant, we remove all of the data with negative residual. And we repeat the process again and again until the results of the statistical test show no autocorrelation, or at least 20 observations remain. We stop and we use this function to fit again to all of the data points. And we use this curve as the target trajectory at the branch mark. And you see the blue curve in the target trajectory is lying only on the highest point. And you see that we have several deviations, but in this presentation, we only consider the biggest one at the perturbation. And to quantify that perturbation, a model based on differential equation was developed. The only response variable we model is the actual daily feed intake, which was integrated to the cumulative feed intake later on. And conceptually, in the absence of the perturbation, the daily feed intake is equal to the target trajectory. Once the perturbation occurs, it immediately reduces the daily feed intake, and the reduction in daily feed intake makes the cumulative feed intake deviate from the target trajectory. And we use the ratio between the actual and the target cumulative feed intake as the driving force to trigger the adaptation capacity of the animal. So during the perturbation, this adaptation capacity have the peak to prevent from further reduction and wait until the perturbation is over. And once the perturbation is over, it induces the compensatory feed intake to have the animal consume more feed and recover. So the concept of the model is demonstrated further in this graph. This is the change in the daily feed intake during and after the perturbation in percentage. So if the change is equal to 0%, so the daily feed intake is coincide to the target trajectory and nothing happened. And once the perturbation occurs, we hypothesize that the perturbation have negative and constant impact on the peak. So this reduction is characterized by 3 parameters: the start and the end of the perturbation, which are completely dependent to the environment. And once parameters indicate the impact of the perturbation and also the way the animal perceives the perturbation. So we call it the resistance capacity. It's the immediate response of the peak against the perturbation. And the last parameters indicate the resilience or the capacity to recover. So here are some results. So the 4 parameters we estimated from the model. So the perturbation is estimated to occur between 85 and 130 days of age. The negative impact of the perturbation decreased 80% of the daily feed intake. And because of thanks to the resilient capacity, the animal already compensate partly the impact of the perturbation. Like you see here, it's around 50% of the the animal already can compensate 50%. And the change in the daily feed intake is the combination between the green and the purple curve. Here are the results of the simulation of the model in cumulative feed intake and the daily feed intake. And you see that before the perturbation, the simulation is coincident to the target trajectory, the blue curve. And once perturbation is happen, it's decreased. And after the perturbation, the pig consume more feed to recover, and it's indicated here. So some discussion and conclusion. The model we developed is able to detect the perturbation only by observing the change in the daily feed intake without looking at the origin of the perturbation. And it happens because of the modern technology. We can now observe a lot of data in the high frequency, and we can quantify the resistance and resilience. The further future work could focus on comparing the response of different pigs in the same environment, and maybe they face to the same perturbation, and we can see if the animal respond differently. And based on the individual variability, we can try to estimate the heritability of the resistant and resilient trait. And finally, I'd like to inform you about one event we are going to organize in October 11 in Budapest, in Hungary. It's a feed hygiene stakeholder workshop. In the workshop, you can have the chance to discover feed utility gene, which is the decision support system developed in the feed hygiene project, and it includes multiple monogastric nutritional models, and our model is one of them. Now we are still open for registration, and yeah, if you are interested, please go to feed hygiene website, and all of the information is available there. And thank you for your attention.
Thank you, Hieu. Questions on the modeling approach? One question for now, and perhaps some other questions later on. Karel.
Thank you. If I understand well, you modeled your response to perturbations on the individual animal level.
Yes.
Are there also ideas to take into account that perturbations are also affect other animals, that you use information from other animals at the same moment to more precisely model the perturbation in itself?
Yeah, thank you for your question. At this step, we are developing the concept of the model, the structure of the model, and in the individual level. But after that, we also look at the cause of the perturbation and the response of the animal. For example, if we have the data of the 1-2 weeks of heat stress, it affects all of the animal, and we can compare the response of different animals, and we can see which animal is more robust than the other.
Okay, thank you.